Hey everyone. In this video, I'm going to be going over 5 problems from the AMC12 that have to do with sequences and series. With a lot of these problems, they can seem really scary at first, but a lot of the time you can find certain patterns and recursions that simplify the problem significantly. So let's get into the first question. This problem is question number 8 from the 2019 AMC12B. It reads, let f of x equal x squared times the quantity 1 minus x squared. What is the value of this sum? So this problem can look kind of difficult at first glance since you got 2018 different terms. However, if you take a closer look, you'll notice that like a lot of different alternating sum problems, a lot of these terms will cancel. So for example, f of 1 over 2019 will cancel with f of 2018 over 2019. Since if you plug in 1 over 2019 for x, 1 minus x will be 2018 over 2019, and likewise if you plug in x is 2018 over 2019, 1 minus x is going to be 1 over 2019. So these two are equal, so they'll cancel. So you can generalize this to any two values of x that add up to 1 will have the same f of x value. And since they have different signs, since the sequence is going to be or rather series is going to be alternating, all of these are going to cancel. So 3 over 2019 is going to cancel with 2016 over 2019, etc. And since we have an even number of terms, 2018 terms, everything's going to cancel and we're going to be left with 0. This is question 9 from the 2019 AMC12B, and it asks for the value of this sum right here. So again, with the double sigmas, this problem can seem a bit challenging, but what the AMC likes to do a lot is to throw in this complex notation that if you can actually understand, the problem becomes very easy. And this problem is an example of that. So let's take care of the first sigma first, right? We have sigma of j equals 1 to 100 of I plus j. So basically this means that we're adding up I plus 1, I plus 2, I plus 3 up to I plus 100. So at the end of this we're going to have 100i, since I is just added 100 times, and then we're going to have for j 1 plus 2 plus 3 plus 4 plus 5 up to 100. And we have a formula for this. We have 100 values. The first number is 1, the last number is 100, and we're just going to divide by 2. 100 cancels with a 2 and leaves a 50 in the numerator, and we're going to get 100i plus 50/50. Now we can deal with the second sigma. So this is going to be sum from the sum from I equals 1 to 100 of 100i plus 50/50. So this means that we're going to have 100 plus 50/50 plus 200 plus 50/50 plus 300 plus 50/50, etc. So basically at the end of this we're going to have 100 50/50s. So 50/50 times 100 plus 100 times the sum from 1 to 100. So this is also going to be 50/50. So basically we're going to have 200 times 50/50, and this is going to be 1 0 1 0 0 0 0. So this is going to be E. Next problem is problem number 18 from the 2017 AMC12A. It reads, let s of n equal the sum of the digits of positive integer n. For example, s of 1507 equals 13. For a particular positive integer, s of n equals 1274. Which of the following could be the value of s of n plus 1? There's two different cases for the value of n. One case is that it does not end in a 9. If that's the case, then s of n plus 1 is going to be 1275, and clearly that's not one of the answer choices. So that means that n has to end in a 9 or a series of 9s. So let's take a look at what happens to s of n when we add 1 to a number that ends in 9. Say n is a number like 2, 3, 5, 9, 9, and n plus 1 is 2, 3, 6, 0, 0. If this is n, which it's not obviously because the sum of the digits is in 1274, but hypothetically if this was n, then we have s of n equals 2 plus 3 is 5, plus 5 is 10, plus 18 is 28, and S of n plus 1 is 11. So what happens to S of n and S of n plus 1 by adding 1 to n is going to be the fact that we're subtracting a certain number of 9s and then adding back 1 for the rightmost digit that actually doesn't become 0, if that makes sense. So basically what that means is that 28 minus 11 plus 1 equals 9. And if we solve this, we notice that 28 minus 11 is 17, plus 1 is 18, and that is 0 mod 9. So what we can do is basically try these answer choices to see which one satisfies this property. So let's try 1274 minus 1265 plus 1 is 10. That's not 0 mod 9. So E can't be the answer. 1274 minus 1239 plus 1 is equal to, let's see, 36, I think. And that is 0 mod 9. So we know the answer is D. This is problem number 19 from the 2018 AMC12A. It reads, let A be the set of positive integers that have no prime factors other than 2, 3, or 5. This infinite sum of the reciprocals of the elements of A can be expressed as m over n, where m and n are relatively prime positive integers. What is m plus n? So the first thing we want to do is to break apart the infinite sum into factors that are easier to deal with. For example, we have one factor that involves the multiples of 2, one factor that involves the multiples of 3, and one factor that involves the multiples of 5. So basically what we're doing when we break apart the sum to these factors is that we pick one term from here, one term from here, one term from here to create one of the terms here. So to create 1 over 1, we know that we have to have a 1 in each of these factors. To create 1/2, we know that we have to have 1/2. So for example, to create the 1/2 up here, we need 1/2 times 1 times 1. So basically we're just choosing this, this, and this. Similarly, to create 1/3, we need 1/3 here and 1/5 here. And to create numbers that are the reciprocal of something like 2 times 3 or 3 times 5 or 2 times 3 times 5, we're just going to be choosing different things. Like if we have 1 over 15, we're choosing this 1/3, and this 1/5. If we're choosing 1 over 30, then we have to choose 1/2, 1/3, and 1/5. So basically, to create this with all the factors of 2, all the factors of 3, all the factors of 5, we basically need an infinite sum in each of these groups. So basically, we have infinite sums. This would proceed as 1/4, 1/8, 1/16. This would proceed as 1/3, 1/9, 1/27. This would be 1/5, 1 over 25, 1 over 125. So basically, we just have to multiply 3 different infinite sums. The first infinite sum has first term of 1 and a common ratio of 1/2. This is 2. This one has the first term 1 and a common ratio of 1/3. So this is going to be 3 over 2. And this last one has the first term of 1 and a common ratio of 1/5. So this is going to be equal to 5 over 4. So if we multiply 3 times 3/2 times 5 over 4, the 2's cancel and we're left with 15 over 4. 15 over 4 is already in simplest terms. They're relatively prime. So if we just add 15 and 4, we have 19. And the answer is C. So this next problem is problem number 18 from the 2018 AMC12B. It reads, a function f is defined recursively by f of 1 equals f of 2 equals 1, and f of n equals f of n minus 1 minus f of n minus 2 plus n for all integers n is greater than or equal to 3. What is f of 2018? There's a few different ways you can solve this problem. One way is to list out f of 3, f of 4, f of 5, f of 6 until you find a pattern. But this way is really time consuming and you might also get it wrong. And for a lot of different problems, this actually doesn't work. and you'll end up wasting a lot of time. So the better way is to use algebra to solve this problem. So to do that, let's try to find what f of n minus 1 is. F of n minus 1 is f of n minus 2 minus f of n minus 3 plus n minus 1. And the intention of doing this is that if we have n equals 2018, what we want to do is work our way back to f of 2, which we know, and then work our way forward again to find what f of 2018 is. So if we plug in f of n minus 1 into this equation right here, we find that f of n is equal to f of n minus 2 minus f of n minus 3 plus n minus 1 minus f of n minus 2 plus n. We notice that these two cancel, and we're left with f of n equals negative f of n minus 3 plus 2n minus 1. So next we can move f of n minus 3 to the other side and get f of n plus f of n minus 3 equals 2n minus 1. So, and if we plug in n minus 3 for n now, we have f of n minus 3 plus f of n minus 6 equals 2n minus 7. So what we want to do next is try to find f of n minus 3 in terms of f of n, so we have f of n and f of n minus 6 in the same equation. And the reason we want to do this is to basically have to do less steps in order to get from 2018 to 1. And let me clear some space real quick. So we have f of n minus 3 is equal to negative f of n plus 2n minus 1. And we get that from this equation. And plugging it in to this equation, we get negative f of n plus 2n minus 1 plus f of n minus 6 equals 2n minus 7. The 2n's cancel, and by moving the 1 to this side, we get minus 6. And if we move the f of n to this side, we get f of n minus 6 equals f of the quantity n minus 6. And with this, we can go ahead and plug in n as 2018 and try to solve for, try to get down to f of 2 or f of 1, which we know the value of. So I cleared up some space, and what we can actually do is rearrange this equation to f of n minus f of n minus 6 is equal to 6. And you can leave it like this, but just for demonstration's sake, I think this is a little bit more clear. So if we plug in 2018 for n, we have f of 2018 minus f of 2012 is equal to 6. And continuing to go down by 6's, we have 2012 minus 2006 is 6. F of 2006 minus f of 2000 is 6. And it turns out if we go down 336 sixes, we're going down by 2016. And eventually we'll have f of 8 minus f of 2 is equal to 1. So, is equal to 6. And since f of 2 is equal to 1, we basically just add back the 336 sixes to go back to f of 2018. And this is going to be 2017, which is B. So that's going to be it for this video. If you enjoyed, please leave a like and subscribe. It helps me out a lot. Other than that, if you have any questions, leave it in the comment section and I'll try to get back to you as soon as possible. And yeah, that's it. Thanks for watching.